Okay, I've got an air conditioning unit here where I've got refrigerant that passes through a compressor, then through a heat exchanger, which cools down the air uh, coming through here. Actually, I guess, oh, this is on the outside, so it's actually heating up the air before it dumps it outside out here. Okay, and I want to find, the power in my compressor. Okay, so what I need to do is I need to set my states, which means finding my H values. So we need to find H1, H2, H3, H4, and H5 for my system. Okay, so I'll start with this R22, and again, we are in English units. Okay, so I go to table A22. I'm sorry, R22. Table A. I like to start with the pressure table saturation. So I'm at 80 psi and 40 degrees Celsius. So I scroll down to 80 psi, and I see saturation is 37. I'm above that. Okay, so I go to 40 psi over here in saturated vapor, go down to 80, and I can see my H is 117.36. Okay, that's, no, hold on, not 80 degrees, 40 degrees. Wait, 80 psi, 40 degrees. Sorry, I had it backwards. So there it is, 108.42. It's actually right there. Okay, so state 2 is 200 and 140. So I go over here. Again, I go back into saturated liquid, and I go down to 200, and I see that saturation temperature is 96. I'm at 140, so I'm well above that. So I'm going to come over to my saturated vapor tables. 200's over here. 140 is right there. So my H value is 121.25. Okay. State 3 is still at 200, and now it's at 90. Now again, you remember the saturation temperature at 200 is 96, so I'm actually below this. I don't have liquid. I am a liquid. I don't have liquid table, so what I do is I approximate it as a saturated liquid at the temperature of 90 degrees. So I go into my temperature saturation table. I go down to 90 degrees, and I use my H value right there, which is 36.32. So let me jot down these values before we move on and deal with the air. So this is going to be 108.42. H2 is 121.25. H3 is 36.32. Okay, now I've got air. Okay, now my air table, all I need is temperatures to find my H value. Okay, so I go to my air table, 22, and I have 80 degrees, which is going to be 540 degrees Rankine. My H is 129.06, and then I have, so again, that's 80 degrees, and I have 110 degrees, which is going to be 570. I don't have it directly, but I can interpolate, and I get 136.24, or 26. So let me go ahead and jot those guys down. Okay, so H4 is 129.06, and then H5 is 136.26. Okay, so now to find the power in the compressor, the next step is to deal with my mass flow rates and figure out what those are. Okay, I can find the mass flow rate of the air because I'm given the volumetric flow rate here. So the mass flow rate of the air, okay, is going to basically be AV4 divided by the volume at 4, the specific volume. Of course, air is an ideal gas, so instead of V, I can use RT over P, okay, which is to say AV4 P4 over T4, right? Again, just using the ideal gas model, PV equals RT. I can get this equation. That's going to give me my mass flow rate for the air. Okay, so I plug in 750, and again, cubic feet per minute. I'm going to multiply that times the pressure, which is 14.7 pound force per inches squared. I need to take that times 144 inches squared per square foot so that I get pounds per square foot on that. Okay, and then R for air, I'm going to use the 1545, and I'm going to divide that by the 28.97. And my units on this, of course, are going to be foot-pound force per pound mass degrees Rankine times the degrees Rankine, which is, again, 540 degrees Rankine. So that degrees Rankine cancels with that. What do I have here? Okay, this cancels with two of those. So I have foot-pounds per minute, foot-pounds, foot-pounds. So now I have pounds mass per minute as my units, which is fine with me. So we'll say this is 55.13 pound mass per minute. So that's the mass flow rate of the air. Okay. Now, I need to know the mass flow rate of the refrigerant. Okay. And I need that mass flow here. Now I can use this heat exchanger. Basically, the chain delta H45 equals delta H23, right? Basically, the heat out of the refrigerant is the heat in to the air, which is to say the mass flow of the air times H5 minus H4 equals the mass flow rate of the refrigerant times H2 minus H3, right? Basically, again, Q into this is Q out of that. Okay, so the heat transfer between those two streams, basically the delta H's have to be equal. So I can plug in all my H values, plug in my A value, and I can find the mass flow rate of the refrigerant equaled to 4.67 pound per minute. So now I've got my mass flows. Now all I have to do to find the work of the compressor, or the power in the compressor, is I just take that mass flow of the refrigerant that I just calculated, and I take that times the change in H here. Again, because it's well insulated, the work is just basically delta H. Okay, so let me go through and make sure we follow the units on this one. So it's 4.67 pound per minute. Okay, I want to take that times 60. Whoops. Oh, I see what I got. Okay, 60 minutes in an hour. I thought I was going to seconds here in my notes. Okay, so anyway, so 60 minutes, and I have pounds per hour times H2 minus H1, which is 121.25 minus 108.42. And again, that is BTUs per pound. Okay, so now I've got BTUs per hour, and my conversion factor here is I have 2545. That's BTUs per hour in every horsepower. So that'll get the units to work out for me when I plug all those values in, I actually get 1.41 horsepower, and that's the amount of work that is put into the compressor. Okay. So again, set your states, find your mass flow rates. I did this one using the definition for volumetric flow over the volume using ideal gas model to get that. Okay. Then I use Q out of one as Q into the other stream to find the mass flow rate of the refrigerant. Once I get that, I just take it times delta H to find the work in the compressor.